coming. We've only got a couple of weeks of the semester left, haven't we? I know the deadlines and things. We're going to finish talking about two things. One is the colour of dyes and how we can predict the colour of dyes. And this is this idea of simple subtractive mixing. So we'll talk about this today. And then hopefully, early next week, we'll start talking about complex subtractive mixing. And this is the basis of, if you've ever heard of colour recipe prediction software. So colour recipe prediction software allows us to measure a piece of fabric, and then using a database of dyes, the computer will suggest a suitable mixture of usually 3 dyes to make the same colour fabric. So the basis of that is something called the Kabelter-Muck model, which we'll talk about. Once we finish that, then we're going to talk a little bit about some textile testing, and that's probably going to be a little easier to think about than some of this stuff. Okay, so I think we finished here yesterday where we'd got an instrument for measuring the colour of solutions, which we call an ultraviolet visible range spectrophotometer. And we take a blank, which is just this clear cell here with the solvent that you put your dye in. So it just depends how you prepare your dye. It could be water. It could be, I don't know, one of the Knolls. But it depends on what sort of dye. So the reason for this blank is just to take away the contribution of any auxiliaries and solvents that you might use, and the glass, the contribution of the glass. So we take 2 of these, one blank, and then the coloured sample that we're interested in. So one of these, and then we pop them into this machine, and there are 2 little presentation stands for them to go on to. I kind of spoke out how this works, but it's just going to measure the light source through the blank, then measure the light source through your coloured sample, and it's going to take away the contribution of the glass and of the solvent. So we're going to hear a few terms. We'll get on to what absorbance is a little bit later, but you might hear something called lambda max. You might hear me say lambda max. And all lambda max is it's a way of describing how the dye is behaving. So lambda max is literally what it sounds like. So we're going to have a different plot to describe our dyes. It's going to be similar in terms of the wavelength axis, our x-axis here. So we usually have 400 to 700 nanometers if we're measuring a piece of textile. Now we might extend that range a bit more. So we might go from perhaps 200 nanometers all the way up to 1500 nanometers. It depends on your dyes. On this axis, we're not going to be measuring reflectance, we're going to be measuring absorbance. And when we look at how absorbance is calculated, we'll find out that the units are arbitrary, which means that we've got a certain range of units, but they're not associated with any of the scientific international units. So lambda max, what's lambda max? Well, often what we find is, instead of being in this 400 to 700 range, many dyes will have a peak outside of that range. And all that lambda max is the location of the peak. Now lots of dyes will have a single peak like this. Certainly a lot of the natural dyes. But some dyes might have something that's a little more perhaps two peaks very close together. So then you have to make a decision on whether that's real or not, which of those two peaks is going to describe the contribution of the dye more. Not usually a concern for us. Okay, so a lambda max value is characteristic of each of our dyes. So that's what I'm talking about when we talk about lambda max. Okay, I think that's all fairly straightforward stuff. Yeah, we don't really cover what we call colour and constitution. We've not got time, but that will be when we start to look at what happens to the light and how it interacts with atoms and molecules, and how that causes changes in energy levels. We haven't got time to really go into that, but there's plenty of sources if you're interested. I can point you to them. Okay, so what's going to have an effect of where this peak is? Well, one thing is what the dye is made out of, its atomic structure. The other thing is what you put the dye into, the solvent itself. And you can have, as I said, more than one peak on your curve. So you can have what we call local and a global lambda max. So here we might have two peaks. This might be a local maximum, but this is the global maximum. That's the highest value. But locally here, that's the local maximum. Okay. As I said before, a lot of natural dyes will have their peak absorbance values outside the visible range, usually towards the ultraviolet. So that's not uncommon, and that's why these instruments tend to be a little wider in their range. And you can also use these UV-Vis spectrophotometers to just do a small range of values. So we might be interested in 300 to 400 nanometers. We can set the spectrophotometer to just read that range. And you might see the term an abridged spectrophotometer. And that just means that we're investigating that small range there. That's all we're looking at. We're looking at that region there. Okay. Alright, so these instruments, they don't measure absorbance. They measure transmittance. What's gone through our coloured liquid. So if we start off here, our light source is here, and this is the intensity of the incident light, the original light source. Then we've got our cuvette, and in our cuvette, our little piece of glassware, we've got our coloured solution. So you'll see the coloured solution here, this blue block. We've got a concentration of our dye, and we've also got the distance that the light needs to travel through our piece of glassware. And then what's going to be measured is what's transmitted, what makes it through our coloured solution and out the other side. Okay. So you can see here we've got the intensity of the incident light, we've got the concentration we've got how far it goes, the path length, and then we've got the intensity of the transmitted light. But we've also got something else called the epsilon, the molar extinction coefficient. Right, this is a little bit, well, it's not difficult, but this is important in understanding how things like Beer's law work and also how Kobelka-Munk works. So the molar extinction coefficient shows the strength that the dye is absorbing the light. Okay? In effect, what it's telling us is how strongly the dye is going to contribute to the colour. So if I have a very weak mixture, concentration of my dye, then actually the dye is not really contributing much to the colour. Okay, so we've got epsilon is the measure of the amount of light absorbed per unit concentration. So it gives us a way of comparing different dyes and how strongly they are absorbing the light. That's useful for us when we start to say, well, we want a certain amount of this dye and a certain amount of this dye. What happens when we mix them together? Okay. So from there, what we're going to do is we're going to calculate absorbance. And it's just this ratio of the intensity of light that's incident, the light that we start off with, our light bulb, and then to the transmitted light. Okay, so we're just finding this log relationship between the incident light and the transmitted light. Okay. So absorbance, the numbers, absorption, the phenomena. These are all pretty simple. They're all basically the same thing. They're just written in a slightly different way. So the transmittance is what's transmitted over our original amount of light. Okay, that's fine. If we want to work out the percent, we're going to multiply it by 100. The absorbance then is this logarithmic relationship, and we can write that in different ways. So we can either take the original intensities of the light, or we can take the transmitted value, or we can look at percentage transmitted value. What we're going to do is use 100. And then here we've just taken the 2 out. 10 to the power 2 gives us 100. So we're taking it out there. So they're all essentially exactly the same thing. Okay. So if we look at different dyes, they're coloured because they're taking out certain parts of the. So if we start with white light, they're going to absorb certain parts of the visible spectrum. So a lemon yellow will take out violet. So that's a little bit of a mixture of some red and some blue. Yellow, well, that's a mixture of red and green, we know that, so that's going to take out the blue. So we can see where, I guess, from looking at our additive and subtractive mixing, those triangles we were looking at before, so we've got Maxwell's additive colour triangle and the subtractive colour triangle, we should be able to kind of estimate where the maximum amount of absorption is going to occur. Yeah. So it might be worth you just having a look at those and thinking about why they are those colours and where the light would be absorbed to give you those colours. Alright, so let's go through the process. Let's pretend we're a little bit of a spectrophotometer. We're going to measure transmittance. So we've got percent transmittance. So what does this mean up here? Well, 100% transmittance means all the light goes through. So we haven't attenuated the signal, we've not changed anything. 100%, the light's gone straight through. 0% transmittance means no light has gone through. You've got a very, very concentrated dye. No light has managed to get through it at all. So if we start to then try and calculate these things, it'll give us an idea of the source of number. And it makes sense. So if 100% of the light goes through our sample, then nothing's been absorbed. If I use 0 up here, I'm going to get an error on my calculator. It doesn't make sense. So I've used 0.1% of the light has been transmitted, and that gives me an absorbance value of 3. So when you start to look at the units for this, you can get an idea of the range. The range is going to go somewhere between 0 and around 3. You've got very, very dark samples. Most of the samples won't be quite that dark. So this gives us an idea. And this is why when you draw these plots, what you'll often see is people will put AU by the absorbance axis, and that just means arbitrary units. They're this strange logarithmic relationship. Okay, so we've got our transmittance and we've converted those values to absorbance. So we measure transmittance, we calculate absorbance. If we plot those now, so if 0 light is being transmitted, we get this value of about 3, don't we? If 100% of the light goes through, nothing's being absorbed. We get this curve, don't we? This curve. So this is percent transmission or transmittance against absorbance. That's fine, and we could probably just use that relationship if we wanted to try to predict how much absorbance we'd get from a particular transmission. But why do we use absorbance rather than transmittance? Okay, so let's have a look at an example. We've got a blue dye which absorbs at a maximum point on the curve at 600 nanometers. So our lambda max, we've got a blue dye, lambda max is about 600 nanometers, and that's where our lambda max is for our blue dye. We'll reduce the path length by 0.2 centimeters for each step. So remember, we've got this relationship where we've got concentration and path length as well, which is the distance the light needs to travel. So each time we're going to look at, well, if there's nothing in the way, all the way up to a centimetre of dye in our cuvette in the way. So we've got a 1 centimetre cuvette, and we're just going to change the path length. What we find is it actually reduces the light by 50% each time. So that means that, doesn't mean that it goes 50%, 100% light gone. It means 50% of whatever we've just reduced it by each time. And you can see this here. Okay, so we start off with 100%, 50, half of 50 is 25, half of 25 is 12.5. You get the idea. If we do the absorbance calculations on that, if we plot it, we get a lovely linear relationship. So if we look at absorbance, against path length, this is how far it's had to go, we get this lovely linear relationship. And we can predict very easily from this straight line relationship what our absorbance will be for a given path length. Okay. So we started off with something that's non-linear, this curve, and just by converting the transmittance values to the absorbance values, we get something that's a straight line, which means it's trivial to calculate what we need. This leads us to think about modelling now, how we can model what happens when we mix dyes together. So we're going to start talking a little bit about colour models. What we're trying to do each time is make the models as simple as we can, as easy to use as we can. So we're going to try to create, just as we did in that previous slide, linear relationships, where all we need to do is make a relationship between two variables so we can fit a straight line through it. For these to work, we need two things. We need the results to be scalable, and we need them to be additive. So when we look at linear models, and this is true for what we're looking at today, but also for Belker-Munck as well. So we want a linear model. So we can use these straight line relationships that make our jobs at prediction much easier. Scalable. So what we'd like to be able to say is if we have a dye, so if we start off with a blue, for instance, hopefully, so we start off with something where so down here we've got a low concentration, up here we've got a high concentration. Hopefully all the peaks here line up so that the peak values from our different concentrations of dye all line up. But if we were to divide each of these curves by their maximum point, then they would all range between 0 and 1 for that maximum point. Hopefully they'd all sit exactly on top of each other. And if that's the case, then to predict one of these curves, all we need to do is multiply it by a factor. Now another way of saying that is a scalar. So that's one thing. Can we predict one of these curves by using a scalar? So that's one thing. The other thing is, if I mix together more than one dye, will they do something sensible? And this is the idea of adding together things, so additive. Will they do something sensible? So if I've got two dyes, and one of them absorbs there in the blue, and the other one absorbs there in the red. If I add them together, hopefully they'll do something sensible. So I might get something a little bit like that. So if I add their contributions together, they do something sensible, instead of, if they added together and then they gave me that, that'd be a bit weird. So what we're after is sensible mixing of these two dyes. And essentially what it says is that these two dyes are independent of each other. So that if you mix them, then they will just produce their greatest absorbances where the peaks would be for the individual dyes. Okay, let's try and kind of go through that. So here's the scalability thing. You can see here at different, this is a monitor, but the same thing holds. At different output levels of that blue channel, we still get a very similar shaped curve. And if we were to take the peak values for all of those and do something called normalization, then they should all sit on top of each other. If they do that, it means that we'll be able to predict different amounts of them quite well. If they don't, then we can't. It doesn't work very well. Okay. So what's the point? The point is that now we can start to do algebra with dyes. So we can start to do simple mathematical sums. What happens if I add a certain amount of this dye to a certain amount of this dye? And hopefully the prediction will be close to reality. So let's have a look at how we can do that. One of the biggest problems that we have with dye baths is that they are nonlinear. So they build up very quickly at the beginning. So if we have a look at this is the contribution of the dye, the concentration in the dye bath. This is the effective concentration. We start off with a white piece of fabric. So down here is a white piece of fabric. As we add dye to the fabric, it very quickly changes colour. So we start to get a very rapid change in colour as we go up here, until we get to a point where we can't get any more dye onto the substrate. It just won't go any darker, it won't get any more colourful. So the effective concentration is the level that we can get to. We can't get any more dye onto that fabric, regardless of how much the concentration of the dye is in the dye bath. So the dye bath concentration might be much higher than the fabric can absorb, much higher than the fabric can take in. And it leads us to this non-linear, this curve for this relationship. And we'll see this relationship quite a few times now. Okay. So subtractive colour mixing. We know we're starting off with white light, and then in our case now at the moment we've got some dyes. Those dyes will absorb some of that white light energy. There's a couple of things that can happen. One is can be absorption and scattering, but for simple subtractive mixing we're just interested in the absorption. If we add in the scattering components, then that's when we're talking about complex subtractive mixing. So simple subtractive mixing is about dyes, solutions, glass, gels, perhaps clear plastics. What do we do then? How do we work out if the system works or not? Well, this has been done really before. It's not something that we need to do, but if we were to test the system to see if it works properly, then we produce a set of samples and then we look at our predictions compared to those samples. The first thing we do is we take individual dyes. So we take the individual dyes and then we make either different concentration solutions of those dyes, or we change the thickness of the same concentration of those dyes. This is an idea called a tint ladder, a thickness series, or a colour ramp. Okay, so this is about working out whether your dyes will mix together properly, really. So we start off with single dyes, and we look at a range of concentrations and a range of thicknesses for those. And then we can have a look at mixtures. What happens when you actually mix them together? Right, let's keep going. So, you'll hear three names. So we've got Bouguer here, but if you were educated in this country, you'd have heard of somebody called Lambert. So we've got Lambert. Who essentially rediscovered the same thing. So what he did, he did. That's it. So this is this logarithmic relationship here. So he's looked at the transmission of light through a transparent body. Okay. So he's interested now in thickness. So the thickness. So he's varied the thickness and kept the concentration the same. And if you do that, you can see this interesting relationship here, this logarithmic relationship we get as the light goes through a greater and greater distance. So glass, he looked at glass, different thicknesses, and this is what he found. So if you use the same concentration, and all you're doing now is varying the distance that the light needs to travel through, he found this relationship. So the transmittance equals the internal transmittance to the distance. So we can see here that 50% of the light is getting reduced each time. Now, in his theory, he talks about actually taking, we can either take 3 centimetres as a block or 3 centimetres individually. It's okay, but we know better than that. So that bottom case there, we know that every time we go from one refractive index to another, we're going to lose a little bit of light. So actually here, although it might be close to that 12.5%, we've lost a little bit of light each time we've gone from glass to air, from glass to air. Okay, so each of those, the distance has this exponential effect, so that we can convert that to absorption. So 1760 now, Lambert rediscovers Bouguer's law. So this is about absorption and thickness. But a little bit later, so we're in the 1800s now, Beer finds a similar relationship. Now to me, Beer's an interesting one, because his relationship says, okay, if we keep the thickness the same, the distance, the path length the same, and we vary the concentration of our colorant, then we find something very similar. We find again this logarithmic relationship, but now with concentration. So you might think about beer having a certain concentration, but this is about, beer is about fixed thickness, varying concentration. that gives us this relationship, which you may have seen at school, but I'm not entirely convinced. You've got the absorbance at a particular wavelength is given by A, B, C, or you might have seen E, C, L. Seen either of those? Anybody do chemistry? So you might have seen either of those representations. So C's concentration, B's path length, and this is the extinction coefficient, or sometimes known as unit absorptivity. So this tells us how far the light has to go. This tells us how strong the dye solution is. And this one, so the concentration of the dye solution, and this one tells us about the contribution of that dye. Does it contribute a lot? Does it contribute a little per unit? Okay. So if these guys are right, it leads us to a nice relationship that says the overall absorbance is equal to the absorbance for dye 1 plus the absorbance for dye 2 all the way up to the absorbance for dye N. So that's nice, that's good. And we can replace these with the ABCs for each of them. And we start to get something that's very easy to allow us to predict the colour of our solution. So just to finish with Beer's law, we've got this exponential again, where we've got our overall transmittance is given by the internal transmittance to the power of the concentration. Okay, so let's test it. So the first thing we do is we produce a colour ramp, and we see whether we've got scalability. We see whether at different concentrations we get the same shaped curve, but at different amplitudes, different heights. If we then normalise those, so we divide by the maximum values on each of these curves, if they all sit on top of each other, then we know we've got this scalability. Okay. Additivity. Okay. So what we're going to do is we're going to go through an example now. We're going to use a UV vis spectro, and that's going to have taken our measurements. We're going to shine the light through the cuvette with the sample, and we're going to measure the transmittance and calculate the absorbance. We're most interested at that peak absorbance value, that lambda max value. So that's generally what we're going to select. Okay, that gives us the best representation of each of the dyes. So we have to look at where they have their peak in absorbance. Okay. Often we're going to use some reference standards as well, just to check that the machine is measuring properly. So we've got certain recipes that we can use that will tell us whether the machine is making the right measurements. Okay. So once we've got our data, we can put it onto our Excel. Hopefully we'll get a nice linear relationship, and we'll just fit a line through our linear relationship. We'll analyse the known examples, and then we'll try and predict some unknown ones. Okay. So we've got absorbance on the x-axis here, and we've got concentration on the y-axis, and we're going to fit a straight line between these 2 points. Okay. What you'll see is the fit up here, and when you do your projects, your dissertations, one of the things that we look for from you is your data analysis and how confident you are in any trends that you see. So if you have a fit here, and we've got a straight line or a linear fit, we have the equation up here, and then we have the correlation coefficient up here, r squared. The closer that r squared is to 1, the closer these points will be to the line. So 0.94, 94% of the variance there being explained. Not brilliant, but not too bad as a prediction. Okay, so that's pretty straightforward. Just have a quick read through that. Okay. Everybody expects the relationship to be linear all the time, and it isn't necessarily. There can be times when it fails. Generally, for the dyes that you guys will use, it's not a problem. But the law is very simple, and it can fall down to 3 real main reasons. So the law is very simple, that's the real. Chemical species might be a bit more complicated than the system was designed for, and the instrument might not be measuring properly. Now, why might that be? Because of what's in the solution, basically. So you need independence. So one dye doesn't cause a reaction with the other dye. The medium that they're in must be the same throughout, and a fancy word for that is homogeneous. The medium mustn't scatter, so there shouldn't be lots of little particulates in it or anything like that will start to make it look a little bit milky. The incident ray should be parallel. The ray should be parallel and monochromatic. That's why when you listen to these machines, you'll hear because they're changing the filter so that one wavelength goes through each time. Okay. And then they can't do anything fancy, like you can't have fluorescence or phosphorescence or anything that's going to cause light emission. Okay, let's have a look at an example. So we've got some dyes here. We've got a yellow dye. So the yellow dye is absorbing strongly here in the blue. We've got a blue dye, and then we've got a mixture of the yellow and the blue dye. So we've measured the values for the yellow dye, we've got measured values for the blue dye, and somebody's sent us the values for the green dye. What we need to do now is work out how much of the yellow dye and how much of the blue dye make up the green dye. So for this, you need to know a few things. We know that the Y sample has 1.38 units of the yellow dye. We know that the blue has 1.07 units of the blue dye, and the green we don't know. We don't know what's in it. So we've got to work out how much of the yellow and green's in it. Okay. So the first thing to do is to have a look at the two dyes and see which wavelength is representing each of the dyes well. So as a default, what we do is we choose lambda max. So where would lambda max for the yellow dye be? Where's the peak value for the yellow dye? About 420, somewhere around there. It's about there, isn't it? For the blue dye, well, we can pick a couple. We could pick this local minima, or sorry, local maxima even, or we can choose this global maxima here. So we could pick a couple of those. Now, if the two dyes are completely independent, which is what we want, then it shouldn't matter. But actually what we're interested in doing is finding a point on each line where one dye is absorbing maximally and the other dye isn't contributing much at all. So we're looking for large differences between the two dyes. Okay, so we kind of got two areas. So we're going to pick about 415. We could pick that local maxima, or we could pick the global one. So we can either go for 610, 630, or 670. First step, read the absorbance values at those points. So once we've got the absorbance values, we just read these straight off the graph. Okay. So at 415, y should be about 1.022. So at 415, y is about 1.022. Yeah? And so we've just read these values straight from the graph. The next thing we need to do is see how much each of them contributes in terms of the units. This unit absorptivity. So we've got A, B, and C. We assume that the path length, this one here, is the same for both of our samples. So we could set that to 1 centimetre, for instance. So essentially, if we set that to 1, we don't need to worry about it. We could set it to the whatever, but as long as it's the same thing between the dyes, it doesn't matter, it's just different. So we know the concentration because we've been told. We've read this value off the graph. So this is the value, the overall absorbance we've read from the graph. This is 1. The concentration's been given to us. So this is the only thing we don't know. So we don't know what this is. And that's what we're going to work out here. So as we've got values for this one, and this one, literally all we have to do is divide this by these two. And that gives us these values here. Right. So we've got a nice simple mixing law that says the absorbance of the green is made up of the absorbance of the yellow plus the absorbance of the blue dye. We can, instead of writing them in big A's as the overall absorbance, then we can use our ABC representation. So we've got the unit absorptivity of the yellow times the concentration plus the unit absorptivity of the blue times the concentration equals that overall absorbance value of the green. We've got 2 points. So we've got a point at 415 nanometers. And if we substitute the values that we know into here, then we've nearly got everything we need. We've also got information at 630 nanometers. Again, we can substitute the values in that we know. So now what we need to do is we need to cancel these simultaneous equations so that we can calculate the values. And obviously there's a couple of ways you can solve this. You can either take one from the other, or you can substitute the right values in. So we can just work our way through and work out the concentrations of the blue dye and the concentration of the yellow dye. So we can work that out. So we know how to make that green dye. So we need a concentrate 0.78 for units of the blue dye, 0.743 units of the yellow dye, mix them together, and we'll get that green. Okay, and I think that's that. So next time we'll start talking about the Kabelka monk and recipe prediction. And as I said at the beginning, after that we'll start talking about testing textiles, which is probably a little bit more what you're used to doing. Has anybody got any questions? Have a go. It's a little bit intimidating when you first see it, but actually once you start working your way through, it's a bit boring. It's a little bit like doing the calculations for X, big Y, big Z. It looks intimidating, then when you do it, it's really trivial. So have a go, have a go, have a go. Okay. All right, thanks for your attention.
I wasn't quite sure if you were just sticking to that time now.
When was it?
It's 11 I'm about to eat it. I wasn't just waving for about 60 seconds.
Whatever I do,
Behave yourself.
no, give me a good grade or the banana.
I've got a lecture at 12. Blah, 10:30.
I could try for 10:30.
Yeah, otherwise it's...
Yeah, no, we can do 10:30.
Otherwise it's... Otherwise it's 1.
I'll do 10:30.
But it'd be about... Yeah, okay.
Yeah, because then I'll make myself stay here and do work for a few months.
Well, we've got lectures.
It's okay. It's a win-win. I'll stay till the lecture and do work in the week.
Right, that's perfect. Right,
You have a
10:30.
submission by then.
What submission?
Any possible submission.
Yeah, 25th. Got one.
What's that? What have you got?
We've got Jackson Lee on the
Jason
25th.
Lee is 25th, which is on 500 words. Then we have another one which is 600.
Biomedical textiles.
Oh, okay.
It's not some like surprise course book for your course.
Right, no, you're not getting anything surprising from here. So,
I was going to say we have to practice testing.
yeah.
Yeah.
Talk about that in the lecture. Right, party.